be simply an operation, like for example, this is components of vector A, and this is components of vector B. So basically, when you add two vectors, you perform per component operation. So if this A1, A2, this is E1, E2, then the sum operation will be A1 plus E1, A2 plus E2. So this is pretty obvious thing. So this notation saves us some indices. Yeah. So we don't have to, when we write this fancy mathematical expression, we don't have to write about the loops. Yeah. So basically, this notation assumes that like for I equals from 0 to size of vector A, phone addition and put that to the C. So that's why it's convenient to use mathematical concepts during the explanation of artificial intelligence topics, because this basically saves us space. And especially this is important when we have more loops. Like for example, if we need to add a set of vectors, that would be a nested loop. Yeah. So for example, we want to add both vector A1 plus vector A2 plus vector A3. So this is already two-dimensional operation, yeah? So we have a set of vectors here, and each vector has some number of components. The important thing that when we add numbers, when we add vectors, each of them must have the same number of components. You cannot add vector with 5 components to vector with 3 components. And to the people who came here, don't worry. I did not yet start the presentation. We just use this amount of time to recall some mathematical concepts to ease the understanding of the presentation. So, for example, we can write, for example, vector S as a sum of these vectors with the Greek summation sign. So we can write like I equals from 1 to m, and we write the index of this summation as the index of this letter AI. Basically, this notation means that we have a table because the columns of this table are the components of vector A, and the rows of this table are different records, and each record is like first row is record A1, second is record A2, third record A3, and so on. So we have this table. So basically, as soon as we write this mathematical expression that I circled, we immediately must understand that this represents some kind of mathematical thing. Sorry. I have a bad habit of walking there and forth. And this thing here might cause some trouble, so I try to fix it. Okay, so we still have a few minutes, so we'll be probably waiting for the other people to come. Now let's, to fill this 5 minutes gap, let's also recall this concept of vectors representing points in space. So for example, if we have a vector x with components 3, 1 or 3, 5, then then we can use the first component of this vector as the first basically coordinate. And we know the system of coordinates not x, y, but we will note it as x1, x2. Why that? Because in practice, vector x might have 3 dimensions, 5 dimensions, 10 dimensions, or even 1,000 dimensions. So when we make sketches like that, 1, 2, 3, 1, 2, 3, 4, 5, yeah. That's where the point corresponding to this vector resides, approximately. So when we talk about multidimensional vectors, we can imagine them as points in multidimensional space. So these, crazy scientific fiction stories about, traveling in multidimensional spaces and, hyper drives and so on. There are some really complex understanding that multidimensional spaces is something unbelievable and impossible to understand. But usually, when we will use the concept of multidimensional vector, you should not be afraid of that. It's just a vector of components more than 3. So two-dimensional vector we can put on a two-dimensional chart. Yes, three-dimensional on the three-dimensional chart, and multi-dimensional vectors we cannot represent visually, but it's all right. We can still think in our heads that these are some kind of points in the space with many coordinates. Okay, so it's now time to start the presentation. My name is Pawel Skribtsov, and I've been asked by the organizers to tell a few words about myself. I run a team in Moscow which works on different artificial intelligence algorithms for different clients, and the basic core mathematical engines and algorithms are so generic that enable to apply them in various fields, like in classifying objects from the LiDAR point clouds, detecting and recognizing human faces, finding trademarks in video sequences, identifying foreign objects in X-ray images, looking for keywords in audio speech, reconstructing three-dimensional objects by two-dimensional pictures, and so on. Many of you are web developers, and web also is a big application field for AI. Well, a simple example could be like, for example, your website has a customer, and you know something about it, like you have some information about that, and you can characterize some customer with a set of features, and you might be willing, for example, to determine based on the features of the client, like will it return again, will it be interested in certain products in your site. All these questions can be interpreted as pattern recognition tasks. If you know a certain amount of clients who came on your site and did certain selection, then you can train artificial intelligence algorithm to use this knowledge to predict the behavior of your future customers. So web is also a big application field for that. Let's think about artificial intelligence as of some kind of program. Yeah? Anyway, it's computer who runs the artificial intelligence, and computer runs programs. So the question is, for example, we want to write a program that needs to differ between can we imagine how the software may look like? Well, from the architecture part, it's easier. Yeah, there's object classifier who takes features of the object, and it must return class label, for example, 1 or 0, or -1 and +1. And in theory, we can just write some kind of function like int cat or dog, and some input features go over here as arguments, and then some kind of if-else nested sequence that we might try to imagine based on our understanding. Like if the tail is longer, but the the head is smaller and the fur is longer, and so on, then return cat. Otherwise, return dog. But you can imagine, yeah, that's trying to define all these relative constants over here, and trying to manually imagine all these if-else sequences would lead to a very complicated program. So programs like that, and every developer sometimes have a function like this. Chasing for this parameter, let me try 2.5, let me try 2.7, or better, now 2.9, and so on. Oh, with 2.9 I have that program, so let's add another constant over here. Yeah, so such kind of code is extremely difficult to maintain. For some problems like cat and dog, I would not even bet for writing such code. It's not reusable, and it's extremely unstable in even slight change of task. So, for example, if we say that lions are also cats, yes, and these African dogs is also a dog, yeah, then all our effort that we spend here is in vain. We will have to rethink and rewrite every line of code. Imagine finding a bug in one of this code, in those lines of code. So we need a totally different approach to solve such problems. Now let's try to look at ourselves. We are human and we are solving such problems very easily. This is the situation when mom teaches its daughter to differ cats and dogs, how it's going on, yeah? There is some book, and we show a person, for example, we show this child a picture of dog, and we ask, what is that? And the baby says, la la la. Mom says, no, this is not la la la, this is a dog. Okay, the next page we turn, there is cat. And the mother asks, what is that? And the baby said, this is dog. No, baby, this is not dog, this is cat. So we turn pages on, and finally, baby learns to differ cats and dogs. Isn't it a miracle? We didn't supply any kind of algorithm to this little wonderful brain. We just showed samples, and some kind of algorithm was born inside the baby's mind without our help. So isn't it what we would be willing to do in our software? Yeah, for some complex computation, some complex if-else nested sequences, we would be willing not to do this for ourselves, but rather just have our computer learn by example. Let's analyze what happened over here. So we demonstrated baby some set of examples. These set of examples were observed. The teacher, who is a mom in this case, supplied class labels. Like when we showed the picture of dog, we just not only showed the picture of dog, but we said it's a dog. So this is called class label, and it was provided by the teacher. So in general, stepping aside, this can be called so-called supervised learning. There's another field of artificial intelligence called unsupervised learning, when the system is about to try to extract different classes without teachers' class labels. But this is a totally different story. Unfortunately, we won't have time for that. but those of you who would be able to understand this presentation will gain enough support to then cover the other subjects of IE by yourself. So in the end, some form of understanding is formed in the way it is mined. Note that important case that particular examples are not memorized by the baby. Or for example, every of you know perfectly the face of your mom or of your brother, and but try now to take a sheet of paper and sketch it. Yes, it's very difficult to do. Without special education, we cannot reproduce the examples of the objects that we used for learning. Nevertheless, we can differ from one person to another. And again, no algorithm was supplied by the teacher. Now, let's formalize the training process, which also seems quite simple from the first approach. Now, we can specify this as a process which takes training sequence as its input. Now the question is, what is the output of the training? And usually here I use, sometimes I give lectures and I use one of the students to be an experimental creature with real intelligence. But to save time now, we will have a virtual body here. Let's call him John. So this is John, and let's make a certain experiment on human. We supply John an image of some object and ask him, what is this class? So John says, let's say it's class 1, I don't know, yeah? All right, now we supply John a training sequence. Yeah, we say, look John, the carrot at class 2, this means potato and is class 1, another carrot is class 2, and another potato is class 1. He says, okay. Now, we repeat our question. We show John carrot, and he says, yeah, it's 2. Now, let's analyze what happened. So there's John before training, and there is John after training. We all consist of molecules, yes, and atoms, and putting away right now the religion aspects of humans, let's talk about humans as being physical systems. Yes, and physics teaches us that if identical system is put identical input, then it will produce identical output. Now we see that the system called John first received this kind of input and and got this output, and now it gets another output for the same input. So this means that something has changed in this system called John. Yeah. So I wonder if you can tell me what is the change. So is there anybody who is willing to tell the answer?
Yeah, he's learned something.
Right, but what does it mean in terms of physical system? Like, he didn't have another ear grown, or like this.
Is more connections between the axons and the brain?
Yes, exactly. So something changed in the neural network of this system called John, and after this change, it started to react differently on such input. Note that neural network existed in John before the training and after training, and nothing has changed in that system. It's very important to note that, because there is no new software program that has been written here in this mind during the training. It means that mechanism of recognition is fixed, and that's the wonderful, fact. Yeah, we don't have to write new program each time we solve new task. So if we call the state of neurons, classifier state, yes, in this John example, we can see that the output of the training process is so-called state of the classifier. So training changes the state of the classifier, and if we could, dump the state of John's mind and then upload to the clones of John's, then we can, receive necessary numbers of classifiers of solvers of this test. Now let's try to join these two processes together. We have a process of training, which outputs the classifier state vector, as we say, and we call it with, we name it with letter W. Why W? Because it can be associated with weights and neural network. And then this is some kind of control signal that controls how exactly the fixed architecture classifier would transfer input data, that is input feature vector, to the class label. There is also some small notation on formalizing the training sequence. We can imagine it as two sequences with corresponding index I. One is input feature of the object that was used for training, and the corresponding class label. Like, for example, features 1, 2, 3, class label A. Features 2, 5, 1, class label B, and so on. So this can be represented as a table where you have columns features, then last column is the class label, and one record is the training example. We will return to this in a moment. Now compare this with a nice analogy. There's a there's a radio receiver, and radio receiver has its input, like radio wave here, and its output as the sound. And the radio receiver has a set of varying parameters. Now, we can tune the radio by varying parameters and change how input, which is basically the same, yeah. Nothing changes in the composition of radio waves here. How it is transformed to the sound. Being turned on one radio, we hear one sound. Turned by another radio, we hear another sound, and we can also adjust volume, and we can adjust timbre. Then this is very much like the classifier works. The architecture of the classifier is fixed. Like when you turn it to a different radio station, you did not make any change in electrical connections in it. You only change some parameters to achieve necessary output, necessary transformation of input to the output. So this is very much the same like the training changes the state of the classifier to adjust how exactly it transforms input vector to the class label. Now let's continue formalization of this task definition. So as you remember, I just told you about the training sequence, yeah, which is a sequence of input vectors and class labels, and we denote the number of examples for training with a capital M, and you can memorize that because it's example, so that's its M. Now, index of class we denote with letter K for the sound class, K class. Now, index of input feature we denote with letter M. So vector X containing features of the object that we want to recognize has n capital components. And as I said, training sequence therefore can be represented as a simple table. Here is the number of the row. This is optional column, of course. Now, columns representing the features of the object, class labels on the right, and one record is basically one full formed training example that has the features of the object and class label. Now, guys, we are ready to start actually studying the first recognition method. And it's one of the simplest, sorry, a little bit getting hot here. And so the easiest method of recognition is the recognition by prototype. Now, what is a prototype? If we think about it, everybody from us see in our life, for example, different tables and different chairs. But if you asked, what is a chair, then you don't imagine a particular this chair or the chair which is in your kitchen. You imagine something average, not too high, not extreme kind of chair, something like that. Yeah. And the same goes with table. It means that we humans have a mechanism of abstract thinking and assigning, associating objects with some kind of meaning. And this was, by the way, analyzed very long time ago. The Greek philosopher Platon has defined that we humans can represent this of two worlds, like our physical world, where actual physical objects live, and then another world, the world of ideas. And so he said that each object is connected with this idea, and that's how we people operate objects. This is also similar to the class-object relationship of the object-oriented programming. And sometimes I explain to my students that we people incorporated these algorithms of object-oriented thinking and differing between particular objects and their ideas, their idealized representation, even in our language. It's a little bit funny that I usually use example of English language, and here everybody is familiar, of course, that we can say that bring me a table, bring me a chair. Yeah, it does not really, when you say a chair, it doesn't really matter what kind of chair you will be brought. Here you mean the idea of the chair. And if you say give me the pencil, give me this pencil, you mean a particular object of the class. So we see that we humans operate this in our everyday life. So how to incorporate that into mathematical engine and use for recognition? Each recognition method can be divided in two parts. One part is training, and the other part is actually the recognition, the computing output from it. As we say, basically this is a representation of two processes that we define. So training by the prototypes can be represented as first computing the prototypes, as its name suggests. So prototype we define as the average vector among the examples of such class. So how we compute average number? We add them and divide by the count of the numbers we add. So the same thing with the vectors. We take a few vectors from our training sequence belonging to this class and make add operation on them. And after that, we multiply the resulting vector on the 1 divided by the number of vectors of this class. Now the recognition is rather simple. We measure the difference between a vector corresponding to the object we want to recognize and each prototype. So we subtract subtract two vectors and then take its magnitude. Then this value can be represented as the distance from our feature vector to the prototype. And in case of this particular method of recognition, we can represent the state, the computed state of the classifier as just the set of its prototypes. Now let's try to understand it with less mathematical notations on a simple example. So suppose we are given this training sequence, just for examples here. And each example has two features in our case, and the right column is class label. So we've got one example of class 1, one example of class 2, another example of class 2, another example of class 1. And now we also have two unlabeled objects whose features are defined but not the class label. And we want to train our classifier using on this full training sequence available with input features and class labels, and then try to apply this trained classifier to fill these question marks here. In general, at this point, I suggest the audience to solve this problem using paper and pencil, and then compare results. So if you are willing to do so, you can try it right now by yourself. If you want to save time, we will go on and I will just show how it's done. So as I see it, we want to just show how it's done. Okay.
Number 5 and 6.
Yes, yes.
And number 6 is
Now,
four.
yes, yes. So let's see what the math notation means. Yeah. So first of all, we need to compute vector average for the features of the first class. So basically, we take this input feature vector and sum it with this one and divide by 2. So this is one feature vector, this is another feature vector, and you can divide it by 2, which means that you divide each of the components. So you get the prototype of the first class. Now the prototype of the second class, in a similar manner, would be the vector 0, 11. Now to compute the difference between the necessary input feature vector and the prototype, we subtract input vector from the prototype of the first class, which is minus 2, minus 3. So 0 minus minus 2 is 2, 8 minus minus 3 is 11, and the magnitude of this vector, which is called norm, is in case if we use Euclidean matrix, is the square root from this sum of squares of the components, which is approximately 11.1. In this case, the distance for the second prototype for this input feature vector is 0, 8 minus 0, 11, 0 minus 0, 0, 8 minus 11 minus 3. We make squares and get the square root from 0 plus 9 equals 3. So 3 is less. The distance to the second prototype is smaller, and therefore we conclude that the object belongs to class 2. And in analogous way, we derive that the second object belongs to class 1. So we can, as I said, we can represent these vectors as points in a multidimensional space. And in this particular example, since the number of components equals 2, we can show it on a two-dimensional diagram. So these are examples of class 1. And and the average of these examples represents to the center of mass here. So this is a prototype of class 1, and this is examples of class 2, and it's a corresponding prototype. Now the two objects that we were to recognize are here and here. And it's obvious that the Euclidean distance is closer to the first prototype in this case and to the second prototype in this case. Well, this is fine so far. And now let's try to apply this to some more complex problem and solve kind of a small optical character recognition task right in front of your eyes. I will use the Microsoft Excel to make all the math, and of course everybody of you would be able to read the formulas wrote in MS Excel and implement it in your own language if you need to, whether it's C# or Java or .NET, so that's why Excel is a very good thing for explaining. So here you can see that we used the 5x5 template to represent small letters A and B. So we have a few examples of these. So these are objects so far, and we cannot feed object itself to the recognition system, like we cannot feed the potato inside the computer. We need to compute its features and analyze its features. So the next step after we have these examples is the forming the training sequence that will contain features of these objects here. So here's how we define the features. So we define the first feature of our object as the sum of the two first columns here. That's just custom designed feature. And the second feature is sum of the three lower rows of this template. So after we define these two features, each object here receives its feature vector. Now let's take a step aside, and you can ask me reasonably why these features. Yeah? From one hand, they seem to be very simple and isn't realistic. From another hand, you may say that why did you use these particular rectangles here? And I have answers to both of these questions. So, isn't this too simple? Yeah, the first question is. No, it isn't too simple, and in fact, this kind of features, when you select some part of your image and compute average intensity in it, in combination with other similar features, it's actually so-called like feature. So you need to remember this name here. And actually the same features are used, for example, in algorithms that detect objects in images. For example, face detection. Many of you know OpenCV, for example, library, where they have face detector implemented. So that face detector actually uses such kind of features. Well, one of the detectors. Now the second question we wanted to discuss is how do you decide, which particular regions to take? And in this case, I just did it with my, brain power. Sometimes we can define good features just with our brain power, knowing the subject well enough. In other cases, like for example, in real face detection, there are comprehensive algorithms that search through the most informative sets of such rectangles. And this is usually a really strong computational effort task acceleration, it may take a week, for example, of computing on a PC. Now with GPUs, all this stuff, of course, may be solved in hours, even in minutes. With a supercomputer, this can be done almost instantly. So now return back. So we have defined the features.
So, can I ask you a question? So you defined one rectangle which is on the left-hand side,
Yes,
and then one rectangle which
Yes,
is on the bottom.
here we sum all cells here. This is feature number 1, x1 we denoted it. And the other feature is x2, is the sum of the lower 3 rows.
So is it important that the two sets cross over, or is that just completely arbitrary because you know it?
That's exactly the question of finding the most informative set of these features. So maybe I'm not that smart myself, and if you play a little bit around with this rectangle, you can define a better combination. But this combination works. It doesn't. Maybe it's not. It doesn't work. In all cases and so on. But it's not important that they cross. They can cross. They cannot cross. You can add more features and make this feature vector 3-dimensional, 5-dimensional. Just too much features is not very good in all cases. There is so-called curse of dimensionality problem that unfortunately we won't be able to cover in this session, but it says that with increasing, we want to do a good thing, yeah? We think that, getting more information about our object would probably increase the accuracy of solving this task, so why don't we start throwing everything that we know about this object in the huge feature vector? But unfortunately here we break by this curse, why it's called curses. You can search for this term in the internet. It's really actively used term. The curse here is that while thinking that you are doing good to a task by increasing input feature vector, in some cases you only make it worse, because with a fixed size training sequence, you cannot use too many input feature vectors. So increasing feature vectors, you must almost exponentially rise the number of examples to train the classifier. There are some tweaks to how to avoid that. That's all about, you can read plenty books and links you can find yourself, but just so far, trust me that, and remember for your tasks, if you start playing with that, too much input features may not always be the best thing to do. So now we define this training sequence, and as we remember, this is a table. As I said, 2 columns represent components of the feature vector, and the second column is the last column is the classifier. Now we compute the prototypes. If you see the formula here, we basically make the sum of the first column belonging to class A and divide it by 5. We can also use another formula of Microsoft Excel called average for that. So this is the first component of the prototype vector of class A, and this is a second component. How we computed second component? It's also a sum of the components of the second feature divided by its number. And this is a prototype of vector B. So the first class has prototype 5, 8.4, and the second prototype is vector 6.2, 7.6 approximately. So here we perform training of our classifier. Now we can make the geometrical interpretation of what the training means in terms of geometry. So here we see blue symbols that represent class A, and the center of mass And the red samples here are the examples of the class B with the corresponding prototype of class B, also denoted as a point in space. Now the most interesting part is that we can make so-called, I call it calculator. So this is a template where we can draw any symbol, and here we compute its features, just the same as we compute features for our training process. This is important, that you always compute features consistently. Now let's see what will happen. I will use a seed for a moment. We start changing our object, and you see that it's now classified as class A. So we can try to modify it again, and it's now classified as B, even though that we have this appendix over here. Note that among our examples, we didn't have that particular example of letter B available. Moreover, we can corrupt it in some way, and it still recognizes letter B. Now let's try to make some different way of letter A. And we see here that in spite of that we didn't have a similar example, it's still classified correctly. How the decision-making rule is formed? Well, basically, this exactly corresponds to the math I showed on the previous slides. So we took, let me double click that. Much better, I guess. So we took this sum of squares of the differences between the feature vector of this object and the prototype of class A and the prototype of class B. And if the distance to the second prototype is smaller, then we say that it belongs to class label B. Otherwise, it belongs to class label A. So you can see that in spite of that, this prototype method is extremely simple and the training is very straightforward. You basically don't need to spend much computational efforts for that. It's already accomplishable in solving some recognition problems. Now let's return back to the boring presentation. Now to a little bit release our minds, let's talk a few seconds about, I will make something intro here. Now let's talk about the applications of artificial intelligence. The interesting question I can give you to think on is, can you identify 4 different fields that represent different reasons of applying artificial intelligence in our world? Well, who can start from the first one? Just any idea? There will be no wrong answers, so you won't be punished.
Forecasting?
Forecasting. Let's see that this is a particular case where we could use extremely educated human experts. For example, in bank systems, there are traders who can watch the numbers and make perfect decisions. Yeah, but what is the disadvantage of having this trader in your team instead of the artificial intelligence? Yeah, you have to pay him. Yeah. So we can generalize this correct answer like the field of when we save money with artificial intelligence, that is economy reason. And in fact, lots of examples that from the first point of view do not directly connect us with economy, indeed connect us with economy. For example, some students answer like security, yeah? But security, in fact, like for example, if you watch all these CCTV cameras on every corner, we can substitute it with a policeman, yes, with a body on each corner, watching around and having its radio and communicating with the central police station. So this solution would work. Would it work? Yes, it would. Yeah, but it's just would cost enormous thing. Yeah, you have to pay salaries, you have to pay vacations, yes, sick days, and so on. So this is also economical example of economical application. Now, can you imagine an application which does not follow from economical reason? One person at a time. I'm sorry, there was some interference here. So, can you raise your hand, please?
Scale. So, if you do processing at massive scale for time, so
Right. That's
you need to process loads of data in a reasonable amount of time.
right. So this is extending human capabilities that human cannot perform due to the just limitation of our brain power. We cannot add numbers quickly and so on. What else? So it's not economy, it's not extending human skills, please. Entertainment, I would say it's closer to either economy if we make the games for the money, yeah, so that customers pay for us, or extending human skills. Let's try another variant.
For medical reasons, analyzing medical images for
Well,
pathology.
I would again suggest that this is economic because we can hire a super doctor who would be classifying the X-rays images for us.
Genetics.
Can you a little bit?
Looking at our proteomics, looking at proteins, trying to find biomarkers. It's not possible with machines.
Well, that's again extending human capabilities. So can you imagine? Can you imagine a case when it is possible to use human? It is cheaper to use human, but we still need AI. Please.
In dangerous areas.
Exactly. Yeah. Dangerous areas, for example, the mining problem. Yeah, it's the salary of the soldier is much less than the Israel's multi-million deminer. Yeah, that you can apply. But nevertheless, from the ethical reasons, we choose to use AI. And now, finally, I would call one of the last field, which is not connected with these three initially.
Just for fun to see that it works.
That's nice, yeah, entertainment.
Because we can.
Well, let's not waste too much time on that. So I would usually give an example of where the human cannot be applied in principle, like for example in far space. Yes? For example, Mars exploration would be better done by human. Yeah, if we could send astronauts to Mars, we would be doing this, and we cannot technically, or we cannot put one person inside the other person so that he studies its intrinsic organs, and we use micro robots for that purpose. Okay, so let's now, after we get some rest, and we can resume that we have studied already one method of artificial intelligence, one recognition method, and you know how to apply it now. Now let's talk about the weaknesses of this. Well, here is the distribution, possible distribution of the samples of the training sequence. So we have one class which has a bigger variety of its input features, and that's why it's represented by a bigger spot. And a small, more condensed class. So actually, if we try to denote each point, how would it be classified by the prototype classifier? Yeah, based on the distance to the prototype, we can easily prove that the decision boundary in this feature space implemented by the prototype classifier is actually a hyperplane which is perpendicular to the line connecting the prototypes and passes through its middle. So it's called the middle perpendicular surface. And so this is how would prototype method would work in this case, and we see that it's suboptimal, yeah? Because definitely there could be a better plane separating these classes, but it's not there where the prototype classifier would implicitly put it. So ideally we would be willing to make a method which would be finding a division between classes in some sort of right way, yeah? Like that. And there is indeed a classifier for that, and it's called the linear decision rule, or perceptron. Now let's talk a little bit about the perceptron. How can we define this? First, let's try to think if we know the position of this line, how we would define the recognition process. So if you remember from your math classes, this is the equation of the plane or line, yes, in two-dimensional spaces, line, in three-dimensional spaces, surface, flat surface, flat plane. In multi-dimensional, we say hyperplane. It's just the weighted sum of the vector components plus one free weight equals to 0. And what does this equation suggest us? If point satisfies this equation, then it belongs to this particular line. So we can see that we can say that W1, W2, Wn, and W0 are parameters that define the position of this line in the space. So now if we look at this expression with more attention, let's try to understand what happens if point does not lie on the plane, on the hyperplane. In this case, it's two-dimensional case, it's a line, but lies on one or the other side of this line. So what happens with this math equation is that on one side of this half space, this expression becomes positive, and on the other side it becomes negative. So when, for example, if we walk from the far distance to the plane here, for example, we would, if we would be measuring this like a temperature, then for example, here we have like minus 10, minus 7, minus 5, minus 3, 0, then plus 1, plus 5, plus 7, and so on. Yeah, so the further we are from the plane, the bigger is the absolute value of this expression. And this is therefore, this is very convenient thing for us to use. We can wrap this expression with so-called activation function f of this kind. That's basically a step function, yes, for all values less than 0, return minus 1, for all positive values, return plus 1. So we wrapped this expression with this function, and now what we have? If we get object, and its feature vector and substitute into this equation. So then for all points on one side of this hyperplane, we will be getting +1. And on the other side of this plane, we will be getting -1. So we can interpret +1 and -1 as the class symbols. Like, for example, letter A would be +1, letter B would be -1. So far, so good. Everything is perfect. Why not doing always like this? And we will return to that. Actually, let me think. Okay, let's, yeah. So why not doing like this? Because it's difficult to find this position. Yeah. If we try to use the brute force, like to enumerate all possible positions of the plane, which are infinite, but though, yeah, we can use kind of Monte Carlo method or something like that. Then each position of the line would be better or worse in terms of the number of mistakes the classifier does. So we can define the function of errors. How many mistakes basically classifier does. So we use this output of the classifier denoted by function f. Yes, and subtract what we get with what we want. The CI, as you remember, is the class label from the training sequence. We use square or absolute function, doesn't really matter, but squares are better. And average by the whole training sequence. So after that, this function of the parameters of the plane, hyperplane, represent how bad is our plane dividing our examples. Now after we made up this function e from the word error, of course, and suppose we would be able to represent it as a curve. We would be willing to find such position of w where this function error has its minima. So basically it corresponds to the best position of the plane we can find. And you can think that, oh my god, how complex would be the code that I need to write to be able to find these positions of the hyperplane. But the good news here that this is very well covered field of mathematics, and it's called optimization theory. And there are plenty of ready optimization engines available in internet, in open source, in some commercial libraries, and it is even implemented in Microsoft Excel. If you know, there is an add-on called Solver, which also does mathematical optimization. Well, for example, in our company, we like Intel MKL library optimizer. There are some open source engines that you can easily find in the internet. There is a link over here in Wikipedia to the list of optimization software. So you can use all of that to find the best position of the hyperplane and train the linear classifier. Now, what is the linear classifier from another aspect? As you can see, it is very easily implemented in hardware, because to perform the computation of the output, we need to take the inputs, each input multiplied by the corresponding weight, so we can use these multiplier units here, and then we can submit the output of this multiplier units to the addition unit. Then we need to shift the sum with this free weight W0 and compute the activation function. As you see, this hardware structure somehow is similar to the behavior of the neurons in the neural network of animals and people, where neuron has dendrites connecting to the other neurons and sensors that we have. And the very, very rough description of how neuron works is that when the input signal coming from different directions exceeds certain signal, the neuron gets activated and starts, for example, its output and activating certain muscle. So this is somehow similar to the our linear decision rule. So this similarity inspired Frank Rosenblatt in 1957. Imagine this number, how long time ago, after the Second World War, to construct the hardware implementation of the first neural network unit. And you see how big it was. It used lamps to perform the logic. But even in this year, the perceptron was able, you can hardly see letters here and some geometrical figures here. These are actually the geometrical figures and letters that Frank Rosenblatt successfully used with this machine to recognize its class. So Frank Rosenblatt is can be considered as one of the founders of the computer implementation of the artificial intelligence algorithms. Now let's try to make this, to repeat Frank Rosenblatt's work in 1957. Frank used this, and we will use Microsoft Excel. So I'm switching back to Excel. So since we don't have much time, I won't do step by step at this moment here, but I will show you how the spreadsheet would look like. Again, we have here the training examples. We have more of them in this case. You can see all of them here. And so again, input features of these training examples are the first two columns. The third column is class label. And at this time, we denoted them as +1 and -1. That +1 will correspond to first class, -1 will correspond to second class. Now, this fourth column is the so-called scalar multiplication of vector weights and input vector, which is that exactly formula of multiplying and adding the input features on the corresponding weights. And here, by the way, we have this, let me show you. Here we have the table of weights of our hyperplane. So hyperplane in 2 dimensions can be defined just with 3 weights. And the equation of this hyperplane, who can call it? How would be written in math? I will help you. It's x1 multiplied by w1 plus x2 multiplied by w2 plus w0. So we have 3 parameters here. Using these 3 parameters here and very simple math, suppose we know x1 and x2, we can compute y or x2, the other components of this points over here. So basically this blue line represents the hyperplane implemented by these 3 coefficients. I will take a seat for a moment and we can play a little bit with that. So you can see that in changing the weights of the hyperplane, we can make it move up and down, change its angle, and then distinguishes between our classes, somehow like that. And as you see, it's quite difficult to do it manually. So we will want Excel to do this optimization work for us. So here is the output of the classifier. As you see, it's activation function which was computed over this mathematical expression representing line expression. And here is basically the difference in square between the output of the classifier and the desirable class number. So now this most interesting moment, we go to the data, we find solver. Let's make it more difficult for him, like spoil the position of the line completely. So now we want to use the solver. So set the target cell here, which is the average of the errors of the classifier. We want to set it to minimum by changing cells these. And we click run. So you see the error was minimized. It was an average error was 1.9 and it's now 0.6. And we've got this perfectly fitting hyperplane that divides in the best way it can our training sequence. Now we can build, after we make this training, and by the way, see here the desired classifier state, that's the correct parameters. We can use the, we can make the calculator which would use the weight to process these input features of this object that we have here. Now look that we used a little bit different activation function. Instead of binary shape activation function like that, sorry, I want so that you can see it. We used the so-called smooth variant of it, which goes like this. Why? Because it's healthy for optimization engine, speaking in very simple words. Because optimization engines which find the best position, they want to see how small changes of the of these parameters influence on our goal function over here. And if it's binary, then small changes sometimes will not give any difference in terms of this value. So it's difficult for them to optimize. Basically speaking, well, more complex speaking, optimization engines usually use gradients and differentiation. So that's why it's better that activation function is differentiation. Yeah. But it was a step aside. Now we can play with our calculator. Again, we can change the appearance of the letter here. Now it looks more like B, obviously because it has more. So you see even corrupted variants have some stability in processing. Make it a little bit smaller. Now I guess, what do you think? Does it more look like B or A? Well, I think that it looks a little bit more like A. Yeah, we can make it this way. So now you can see that we have constructed and learned another realistically implemented method of machine learning called linear decision rule. And I can tell you that real-world engines that run real-world problems are not very far from this. So they also use optimization engine. It's just their function is a little bit more complex than ours. But in overall, the approach remains the same. All of the approaches use training sequence. They use input feature vector. They use training process that minimizes error function with some kind of optimization engine. And it can be hierarchical. For example, you break problem into sub-problems, and then you solve each sub-problems independently, and then you have some kind of mixture of experts who solve more complex problems. Now, let's continue. If you have some brain capacity. What is the problem with linear decision rule? Is that there are some more complex distributional features that obviously cannot be separated by just linear decision rule. And it worth noting other very simple classifier called nearest neighbor, which basically implements arbitrary complex decision rules, not only linear. Behind this math is a very simple concept. Basically, it's like prototype method where we, instead of one prototype, each of our training sequence component is a prototype. So when we want to classify some feature vector, we just search through our training sequence and find the nearest, in geometrical sense, nearest example. And we assign this unknown object the class label of this nearest example in our training sequence. From the first look, isn't that a genius invention? Yeah. The training is trivial. Basically, the training in this approach is basically memorizing this training sequence, and the recognition is simple too. What are the the problems with this? Well, at first, we have to, during the major problem of this is that the speed of processing in this case depends on the number of training sequences, and for some real-size problems you won't be, you will be willing to have like millions of examples. And imagine that for each classification that you need to perform, you have to run a loop of a million multiplied by the number of input features in your vector to make the class labeling. So basically, nearest neighbor classifier works much slower than, for example, linear decision rule or prototype method. Because in that case, please.
I was just going to say, presumably you could post-filter the prototypes to cut and load them out.
Yes. There are indeed techniques that accelerate nearest neighbor finding process in hierarchical representation of the features. Like, for example, if things are very close here, instead of having these 1, 2, 3, 5 here, we can represent just one vector here. But this already leads us to a more complex class of algorithms. Basically, such algorithms start more look like neural networks of the radial basis function architecture, where each node is actually a result of clustering of the input vectors into particular clusters. Now, after we identify the first problem of the long computation, there is a much more serious problem with that. Is that this advantage of fast training in fact means that we didn't really train classifier, and it's more memorization than generalization of knowledge. For example, in this case, the nearest neighbor classifier would work fine. But in real life, we usually have some noise added to the features, or even sometimes noise in the class labels, because sometimes we can make mistakes in identifying class of the object during the training. So, for example, if we change the label here from rectangle to triangle, the linear or prototype decision rule wouldn't much change. But for nearest neighbor, it will take this sample as the as the rule to behave. And in all this set of in all this volume of your feature space, we will have wrong decisions. Now, if there is noise, and for example, this rectangle had to be here, but due to the noise, it has jumped a little bit below. Again, for the linear or prototype decisions, it will just maybe slightly vary the position of this decision boundary. But for the nearest neighbor prototype, this would mean that the whole area of the feature space around this outlier would be incorrectly classified. So be very careful in using a nearest neighbors method. There are lots of improvements over nearest neighbors methods, such as high nearest neighbors. You will be able to read about these methods yourself. The main important thing to understand why do they do all these tricks, and they do that because of such issues that I have shown. Now, what is this can be compared to? I sometimes give this example. Exam situation, and there are two types of students usually. One student has perfect memory, so he spends his days before the exam just reading textbook and memorizing all the definitions. So the other student does not have such good memory, and he wants to understand the subject, so he reads slowly. Usually he cannot read till the end of the textbook because he tries to understand. And but then exam time, yes, and the teacher, when he asks for the first time the first student who memorized it, he thinks that wow, it's something like A. Maybe he can also solve some problem, and here we have a problem, yeah, that he cannot solve problems because he just memorized the subject. So it's important to understand that memorizing does not give us rules on how to differ from one class to another. The second student who spent time in understanding, maybe he not so well answering questions of the teacher, but he has understanding and he can apply this knowledge to solve real world problems. So that's where understanding differs from memorization. For example, you can compare memorization process with SQL database. It can also store samples, it can store the training sequence, but it can only retrieve with either exact match or some human described matches that we can construct. It does not itself represent knowledge of the difference between two classes. So, in order that classifiers generalize well, usually the rule is that the number of coefficients that describe the classifier state must be much less than the number of training sequences. That is basically the memory of the classifier, these three weights that it has, must not be enough to memorize the training sequence. And if it could learn the training sequence with this small amount of weights, it means that it really learned not the examples, but it learned how to diff examples between themselves, between different classes. And this is a compressed knowledge representation on the class differences. And this knowledge representation usually have good generalization capabilities. That is capability of correctly classifying examples which did not originally belong to the training sequence. Now, what is the alternative to that, and how we can apply this lovely perceptron to the more complex problems where we cannot separate with the linear decision rule, and that's where the neural network concept comes from. That it has units of linear decision rules, which each of them implements certain linear decision rule, and then next layer combines the result of the previously classified into the and joins into the common decision boundary. And in this case, we have a compromise because the amount of computations needed for the system also does not depend on the number of examples. It depends on the number of units. So we can find the proper number of units which solves our test proportional to the complexity of the problem. If problem is complex, then okay, we have many units and we understand why it's working long, because it's a complex problem. And if problem is not that complex, then we can have fewer nodes here, and then the boundary will be simpler, and so the decision will not depend on the number of examples. So this is basically how artificial neural networks work like. And I can show you a real-world example that I prepared especially for these sessions a few days ago. It's kind of a weather forecast for London. It's common to ask if there will be rain in London or not. It seems to be like a quite tricky question. So I tried to show you, for example, how to implement the answer on this question with neural networks. So my assumption was that weather is coming from, basically it's coming from different sides of UK, and each of these cities has fact weather information that we can get from the website, plus wind direction, and I think that this is somehow influence what the weather will be in London. We just don't know how exactly it influences. So we formed this as a pattern recognition task. We simplified it for this session, of course. We take it as a binary recognition test. Will there be a rain or there will be no rain? In order to do that, I have made some data mining. Sorry. I used the Meteor Probe website where they can tell you the weather information on the required cities. Unfortunately, they can only give you by 30 days. So I had to manually join a few pages of this information in the Microsoft Access database. You can here see the two rings, means the join operation. I will open this database just to show you how it looks like. So, for example, this is weather in London, Portsmouth, Ashford. Now I have joined them, and finally made a training sequence where, let it work for a little while. So I represented wind direction as also vectors. Like this is, for example, vector +1, 0. This is -1, 0, and so on. So wind direction, average wind directions per day were represented as, for example, CT number 2, delta x, delta y, and so on. And then the rain conditions in these cities are in this column. And then, so we joined all this information into one big feature vector. As you can see, these are just rain information and wind direction in all these cities around London on the current day. And this column is the historical information whether the rain was on the next day in London. So after that, it is exported to this to a text file, and like this, basically tab delimited format, and the software library used. That's a warning that I don't have hardware acceleration on this laptop. That trains a neural network for this data set. So we can look at some features of this output here. So we have loaded the text file. We have 101 positive example that is about 100 examples where we had rain. 158 examples when we didn't have rain. The total number of examples 259. The network had 30 input features. This means that our feature vector was in the 30-dimensional space. Yeah. And now this software constructed complex neural network by small 2x2 neural networks using so-called ADA-boost algorithm. You can read all about that. And finally, after the training took place and we have now run our neural network on the whole data set, let's scroll to the end. Let's see what we have in terms of vectors. Yeah. So among then, so it used only half of the training sequence for training, and then the other half was used for measuring the quality. After the training process, both parts of the training sequence was joined, and this is output on the whole set of examples. So what we see is that we found 102 examples, the decisions that there will be rain, of which only 91 was correct. It corresponds to the about 90% precision metrics. And total amount of positives was 101, so it means that the recall metric is 90. So we were able to correctly find 90% of rain cases, and in all cases that we found, in 90% we were correct. So this corresponds to this error of the so-called first and second kind. So as you can see, even this simple work can result in quite appreciable software algorithms, and for you it's now possible to deploy this in your applications to solve different problems, including web-like problems. Then after the training took place, you have a file with a network. Yeah, it's in the presentation actually. That's the output of the learning process, as you see. That's the classified state. That's the coefficients of the neural network connections, and you can also see the configuration of the resulting network constructed by the algorithm, the number of layers, and so on. And then the code which works with neural network is usually very simple. It's right for any library that you will use. I will then show you some links for the libraries that you can use for your work. So basically, you can wrap neural network object with your some wrapper class that basically loads the network in the constructor from the file, and then basically the main function here is like return confidence of the object belongs to a certain class by invoking a compute function of the network objects with where the features are given as the input array for this method. So it's very easy to use. So for your help, I can suggest two of my favorite books that I like to read before I go to sleep. It's Hiking Neural Networks and Christopher Bishop Neural Networks for Pattern Recognition. These are very nicely written books, and the links are here. If you would like to get the final version of this presentation, because the original one might not have these links, you can write on my email provided in the original presentation. I will send you. I can also help you to ask some questions about your particular recognition tasks if you have some problems in defining or choosing a right method for it. So basically, if some of you use some kind of standalone applications like Statistica, MATLAB, these tools have machine learning engines, including neural networks, support vector machines, and so on. On Linux, there is so-called R project, which have lots of statistical machine learning methods implemented. For C++ programmers, I would suggest OpenCV machine learning library, where they also have neural networks and other machine learning technologies implemented. For C# developers, you can use MNIST library for classifying images. And there is lots of links that you can Google, of course, using the keyword pattern recognition and things like that. So basically, we have got to the end of my presentation. I can just tell you the end word that the world of AI is big, and we haven't covered many things like function approximation, which can be used for interpolation and forecast. But function approximation is very similar to pattern recognition, but it's just when you recognize the value of the function. So basically, this is almost the same as pattern recognition thing. Unsupervised learning is that when you need to determine to define classes without a teacher. Like, for example, people are coming to your site. You want to group them into several groups by similarity. How many groups are there? Who belongs to which group? So on this question, you can use unsupervised learning, which is the same as clustering, taxonomy, and you can use that in, for example, accelerating searches through your databases. Statistical basis for pattern recognition goes basically from the bias theorem, and we didn't unfortunately have time for that. But I can tell you that all these deterministic methods that we covered, linear decision rule, prototype methods, they are private cases of the bias theorem. So these methods that I just gave you for trust, they indeed are derived from the mathematical background. And of course, beyond neural networks, there are lots of other methods that you can now search and understand the difference. I guess that's it. Thank you very much for your attention.